Okay, so today I want to talk a little bit about fractions, everybody's favorite topic, right? If we're going to add, if we're going to add a couple of fractions, let's say we wanted to add like 2 over x plus 1, maybe, and 3, say, over x minus 1. If we wanted to add these two things together, you have to have a common denominator to add a couple of fractions, right? And here we would use the product of the denominators that we have. So the denominator that we will use to add these two things up is x plus 1 times x minus 1. I'm hopefully reminding you of this and not telling you anything new. So you need to multiply the first expression bottom and top by an x minus 1, and then the same thing here, we need to multiply the other expression by x minus 1. When we do that, we have the same denominator, so now we can add all of this up, and 2 times x minus 1 plus 3 times x plus 1, and it all goes over the product of x minus 1 times x plus 1, right? Okay, and then, you know, we could clean this up. So on the top you get 2x minus 2 plus 3x plus 3. And if you wanted to multiply those together, I guess you could. You get x squared minus 1. And then finally, 2x here and 3x here make 5x. And then a negative 2 here plus this 3 is 1. And so adding these two things together, you end up with an expression that looks like this, okay? Who cares? Well, we do, because the thing is, if you're being asked to find the integral of something like this, 5x plus 1 over x squared minus 1, good Lord, I have no idea, right? Except for all of this work that I've done here, I know that this is equal to this, and I think I can integrate that, right? So if I know how to get from here to here, and that's the subject of today's lecture, if I know how to get from here to here, then the integration is comparatively straightforward, right? The integral of 2 over x plus 1 plus 3 over x minus 1, right? These two things are equal to each other. Do you know how to integrate this? If you make u equal to the thing on the bottom, then du and dx are the same, and you end up with 2 times the log of x plus 1 plus 3 times the log of x minus 1. And so the antiderivative looks like this, and you know, who'd have guessed, right? That this is the antiderivative of that. Well, we don't have to guess. So if we're looking to integrate things that look like this, we use what's called the method of partial fraction. Okay, so let's say you had, so let's say your goal is to integrate this function. What do I have? 2x minus 5 over x squared minus 5x plus 6. So that's my goal, and so I want to be able to write this thing hopefully as the sum of two easier to deal with fractions, like I did earlier. So how do you do that? So ignoring the integration part for right now, let's just look at the integrand. Let's just look at the expression. So the first thing that you do is factor the denominator. And that can look really different depending on what your denominator looks like. But this one happens to come apart like this, right? So after you factor the denominator, then there's a theorem, what is it called? It's the fundamental theorem of algebra, I think it is. And it says that if you have an expression that looks like this, that you are guaranteed to be able to find real numbers a and b that make this equation true. So I want to find a number a and a number b that makes this whole equation true for any value of x. And the way that you do this is, well, we're going to add these up. And in order to add these up, the denominators have to be the same, right? And so again, we'll use the product of the two that we have, and we get, let me write this stuff down again, 2x minus 5 over this stuff is equal to, so when I add these up, the first expression will get multiplied bottom and top by an x minus 3, and the second one will get bottom and top by x minus 2. So we get a times x minus 3 plus b times x minus 2, and that'll all be over now the common denominator of x minus 2 times x minus 3, right? Well, here's the thing. If these two expressions are equal to each other, I've already got the denominators equal to each other, right? So the only thing that remains to do is to find a and b so that the tops, the numerators, are equal to each other. So 2x minus 5, I want that to be equal to a times x minus 3 plus b times x minus 2. And I want to find, again, to find a and b so that this is true for any x that I would put in here. And here's a kind of slick way to do it. Well, if this has to be true for any x, then in particular it has to be true when x is equal to 3. Why did I choose 3? You'll see in a minute. If x is equal to 3, then the expression on the left is 2 times 3 minus 5. That's 1, right? And then what do I get here? Well, if I make x equal to 3, then 3 minus 3 is 0, and the whole first term is gone, right? And if I make this x equal to 3, 3 minus 2 is 1, and oh, look what I get. I get that b is equal to 1. So that's kind of cool. And so that's this b up here. And so I can find the value of a by similarly choosing a value of x that'll cancel out this part. So when x is equal to 2, 2 times 2 is 4, minus 1 is 5. I'm sorry, 2 times 2 is 4, minus 5 is negative 1. Negative 1 equals, and if I make this x equal to 2 here, I get a negative 1 here also, so negative a, right? And again, if I make this x equal to 2, then this part is all just going to be equal to 0. So here, oh, so a is 1, right? So a and b are both equal to 1. So what are we doing? Oh yeah, we're integrating. That means that this integral can be rewritten as this integral, 1 over x minus 2 plus 1 over x minus 3. And that's easy to integrate. That's just a pair of logs. Okay, so this is called the method of partial fractions. So here's another example. And so ultimately I want to be, look at this, oh my gosh, it's a mess. Ultimately I would like to be able to integrate this, but first I need to see if I can tease it apart a little bit. So ignoring the integration for right now, notice that I can write the denominator as x squared times x plus 1. And so if I want to do a partial fraction decomposition, that's what this thing is called, on this, I have a linear factor here and it's repeated, and a linear factor here. So in a case like this, for every time the factor is repeated, you need another term in your decomposition so that it looks like this. So if this had been an x cubed, then I would need a over x plus b over x squared plus a c over x cubed. Okay, so that's how that part works. And then I just need a c here over x plus 1. And so now I'm going to add these up. The denominator is going to be x squared times x plus 1, right? The same as it is over here. So I'm trying to get the stuff on the top all to be equal. So this is this this first term, I need to multiply at bottom and top. I need another x and an x plus 1. So I have ax times x plus 1. This term here just needs the x plus 1, so b times x plus 1. And this one needs the x squared. Okay, and so I want to find A, B, and C to make all of this stuff equal to each other. And I can, to some extent, I can do the same thing that I was doing before. That is, I can choose values of x that'll make parts of this go away. For example, if I make x equal to 0, then on the left, I just get a 3. Let's see, on the right, I get a 0 here, right, and a 0 here. But here I get b times 1. So it turns out that b is equal to 3. For my next choice for x, I can make x equal to -1. That should knock some things out of here. If x is equal to -1, on the left I get 3 minus 5 plus 3. And on the right, that term is gone, right, because it's got an x plus 1 in it. That term is also gone for the same reason, and I just get c here. So I get c times 1, and that's equal to 1. So c is equal to 1. And then the last thing left to get is the value of a, and I can't, there's nothing I can make x equal to get rid of everything else. But I can plug these in and see what I have. So let's see what this looks like. 3x squared plus 5x plus 3 is equal to, I'm going to write this ax squared, right? And then ax times 1 is ax. B is equal to 3, so 3x plus 3. And c is equal to 1, so plus x squared. So this part's kind of cool because, check this out. So I say, well, I have 3 x squareds on the left. How many do I have on the right? Well, there's a of them here and 1 of them here. So if these have to be equal to each other, do you see that a has to be equal to 2? So the 2 of them that you have here plus the 1 that you have here gives you the 3 that's over here. And if you make a equal to 2, that means this a also has to be equal to 2. Oops, that's ax, right? Sorry. That means this a also has to be equal to 2, and then I get 2 x's here plus 3 x's here. Oh, perfect, 5 x's. So a is equal to 2. And so, yeah, so this integral, back to the integral now, plus 5x plus 3 divided by x cubed plus x squared dx. That can be written as the integral. So a is 2, so 2 over x. B is 3, so 3 over x squared. And c is 1, so 1 over x plus 1. What do we get? 2 logs of x minus 3 over x plus the log of x plus 1. All right, the last example that I'll show you looks like this. Okay, so in this example, one of the factors in the denominator is it's called an irreducible quadratic, and there's nothing that you can do to factor that. And so let's just look at the partial fraction decomposition of this thing, x times x squared plus 1, like this. And so a over x, right? But when the other factor is quadratic like this, the expression that goes on the top is linear. I know it's crazy, right? So the fundamental theorem of algebra says that that there exist real numbers a, b, and c that will make this equation true. How do we find them? We do what we have been doing. Negative x squared plus 2x minus 1. And then on the right we'll have a times x squared plus 1 plus x times bx plus c. So let's start by trying to make x equal to 0 and see what we get. If x is equal to 0, on the left we have a -1. On the right, out of this, if this x is equal to 0, we just have 1 times a. So there's that. And if that x is equal to 0, everything, all of the rest of this is gone. So we get that a is equal to -1. But now there's nothing else that we can choose to get everything else to drop out. So let's just see where we are, okay? Negative x squared plus 2x minus 1 is equal to -1 times x squared plus 1 plus bx squared plus cx. So negative x squared minus 1 plus bx squared plus cx. Well, we've got the -1 here and the -1 here, so that's good. This is the only x term that we have over here, and here's an x term over here, and if these two things have to be equal, that means that c has to be 2, right? And what else do we need? Oh, b. So I've got a negative x squared over here, and I've got a negative x squared over here, and then b is just right here. These things are already equal to each other. That tells me that b should just be equal to 0. So there are my 3 constants. So if I go back up to my original integral, this means that I can rewrite it as a over x, so that's -1 over x, and then for the x squared plus 1 denominator term, nothing for b, just c is equal to 2. Okay, and this is much easier to integrate than this thing is, and we just get negative log of x plus, do you recognize this? And there you have some examples of the method of partial fractions.